Okay, let's get started. So thanks, guys, for your patience while we figured the audio part out. Good afternoon, everyone. Today, we'll be talking about securing Kubernetes deployment at scale. I'm Sohini Mukherjee, and I am a security partner at LinkedIn. So let's get started. Here's our agenda for today. We'll briefly talk about the Kubernetes architecture. We'll discuss some attack scenarios. We'll explore how we can secure such Kubernetes deployment at scale. And of course, we'll end with the conclusion. So what is containerization? So as the world has moved from a monolithic to a microservice-based architecture, more and more developers are deploying their workloads via containerization, either on-prem or in cloud services. The caveat being, not all such implementations were designed keeping security in mind. That is, not all such implementations are secure by default. Sensitive data can be inadvertently leaked due to various security control failures or misconfigurations. So containers are just lightweight VMs, right? Would you agree? No? Okay, let's see. So how does containerization differ from virtualization? And I'll let you read through the slide. But the bottom line being, containers virtualize the operating system so that multiple workloads or multiple processes can run on the single OS instance, sharing the same host kernel space, right? On the other hand, for virtual machines, it's the hardware that is virtualized to run multiple operating system instances called guest OS. And this is achieved by something called an hypervisor, right? Now, containers don't implement hypervisor and hence are deemed lightweight or more agile way of achieving virtualization and faster resource provisioning. However, it might be fair to state that containers are not secure by default, as in we need to walk that extra mile to make sure that the workloads are secure in a hostile multi-tenant environment. Now let's talk about the architecture a bit. So here's a client-server architecture. On the left-hand side, we have the control plane components, the kube scheduler, the HCD, the controller manager, and the API server. And on the right-hand side, we have the worker nodes. So nodes can be bare metal or virtual machine, and it basically stages the container, right? As in like the container runtime, the kubelet, kube proxy. And pods are the smallest unit of compute in the Kubernetes world. And I would be using pods and containers interchangeably throughout this presentation. Now let's talk about some attack scenarios. So crypto mining and cryptojacking remains one of the most popular attack vectors as far as containers and container orchestration is concerned. And the primary objective being to hog computing resources, right? Now that being said, it comes with an inherent risk of sensitive data being exfiltrated. And this can be achieved if an attacker is successful in breaking out of the bounds of a container and escaping into the underlying host kernel space. So any vulnerability that allows the attacker to modify the underlying kernel data structure can lead to a container escape scenario. And one of the avenues to achieve that is by compromising a privileged container. Now let's look at one such attack scenarios that has been detected in the wild by Trend Micro's honeypot. Now I can't explicitly talk about attacks that I have seen in real world scenarios, but this is pretty close to replicating the standard TTPs that we would see in a container compromise scenario. So let's see what happens here. So an attacker-controlled scanner called zgrab has been, scanning for containers with exposed API. Once such misconfiguration is detected, the attacker would pull and deploy a malicious container. Now, one of the deployment parameters here is privileged, which is one of the requirements for this specific container escape technique. Now, if you're following along with this diagram, the attacker's entry point is a shell script called com.sh, which is towards the middle portion of this diagram. Now, com.sh is executed as part of the malicious container image that we just referred. Com.sh calls Nginx, which is our cryptocurrency miner. Now you can see the attacker innocuously, names the miner as Nginx in an attempt to fly under the radar and, pass off as something legitimate and evade detection. And ultimately, the attacker succeeds in going ahead and creating a mining pool. Now let's talk about our next attack scenario, which is Siloscape. Now, Siloscape is a heavily obfuscated malware that actively targets Windows Server containers in the wild. So before going into the details of this particular attack, let's try to gain some context on how Windows implements containerization. So Microsoft has two solutions. One being running container inside individual virtual machines based on hypervisor. The other, which is the Windows Server container in the context of this particular attack scenario that we are discussing, leverages something called silo objects, which is a Windows kernel feature to enforce isolation. Now, this implementation resembles, traditional Linux, how traditionally Linux implements container isolation with namespaces and C groups that create logical partitions and separation of resources to enable multiple processes being run on the same host kernel space. Now, some users prefer this solution over hypervisor-based isolation because, running each container within an individual virtual machine comes with a performance cost, right? Now, Microsoft has an interesting disclaimer. Microsoft doesn't endorse silos to provide a high degree of isolation in hostile multi-tenant environments and instead recommends hypervisor. If you're wondering why, let's look at the exploit path of Siloscape. So the attacker achieves, the initial foothold via, say, a remote code execution by exploiting a known vulnerability within a Windows container, or maybe compromising a web server. So once that initial foothold is established, the attacker executes Siloscape, which is the binary cloudmalware.exe, if you're following along in that diagram. Now the attacker implements an interesting Windows container escape technique to gain code execution in the underlying node. And how the attacker achieves that is by impersonating a special process in Windows containers called cexec_svc by DLL injection. Now, why I call this process a special process? Because this is responsible for many of the aspects of container execution, and also holds the link between the host and the container. And it also has something called TCB, or Trusted Computing Base Privileges. Now, if a malicious process is able to execute, or impersonate via this special process called cexec_svc, it would inherit all the capabilities of that process. Now, cexec_svc has trusted computing-based privileges, so obviously now our malicious process has also attained the same privileges. Now, TCB privileges are powerful, and that lets our attacker create a global symbolic link to the host, practically linking the containerized X drive to the host C drive. And a successful container escape has happened at this point. Now the attacker, looks into the compromised node if it has enough privileges to create new Kubernetes deployment to be able to run more crypto mining pools. And this is basically an attempt to spread across the cluster. Now, as is common for most malwares, it will connect to its CNC server via the TON network and open a backdoor to run cryptojackers and potentially exfiltrate sensitive data if the cluster was, holding critical information. Now, having discussed, a couple of attack scenarios spanning Linux as well as Windows containers, do you feel the need for a structured approach to be able to articulate risk in our Kubernetes deployments? So Threat Matrix by Microsoft and also the MITRE ATT&CK framework for Kubernetes provides a similar structured approach to define the various attack vectors and be able to define the threat landscape of a Kubernetes ecosystem. Now let's explore how we can secure such Kubernetes deployments at scale. And starting with Kubernetes host. So it is imperative to harden the underlying host by making sure that you are running the latest version of operating system. As important is to make sure that you're running the latest version of Kubernetes as well. And the point that I'm trying to make is, a structured and streamlined patch management and configuration management system is extremely imperative to ensure a baseline security posture of the cluster and keeping vulnerabilities at bay. Because a couple of attack scenarios that we just discussed, the attacker gets the initial foothold into the cluster by exploiting a known vulnerability. Right? And we don't want to do that. I mean, we don't want to get the task easier for the attackers. Talking about control plane security. So strong access control on the various control plane components via authentication, authorization, and also relevant network segmentation is extremely critical. And why I would say so? Because, say for example, etcd. It's a journal. It's something that holds critical cluster information like cluster state, right? So a write access to the etcd can be equivalent to gaining root on the cluster. Even read access to the etcd can help the attacker in escalating privileges pretty fast. What about the API server? It's kind of the front end per se, right? It's the first line of defense against attackers. So the point I'm trying to make is, access should be strongly monitored and also controlled to make sure that the security of the control plane components are ensured. Let's talk about some of the Kubernetes components. Limiting SSH access to the Kubernetes node can help us protect against unauthorized access to host resources. Similarly, restricting access to the kubelet. And also encrypting in-cluster communication via TLS. And I'm referring to MTLS here. Now, you might have a counter question that we are talking about in-cluster communication. Is there a need to encrypt it? I would argue that we are talking about a multi-tenant environment here, right? So there is a need to secure components within the cluster as well. So let's see some of the guardrails that we can implement in the build, deploy, and runtime phase. And starting with image management. So what is a container image? So container image is basically a standalone executable package of software that is used to run any application. Say code, runtime, system libraries, system tools. So what is the risk here? And the risk is to run untrusted code. So it's extremely important that your base images are approved and signed and controlled via central deployment pipeline with a continuous scanning cadence for vulnerabilities. It's recommended to use minimal base image without the unnecessary packages. even in your dev environment, it is dangerous to let users pull and install random images from unknown sources, because it can be subject to supply chain kind of attack where a malicious piece of code or a third-party library can be injected to a seemingly benign image. Talking about secret management, shouldn't be any hard-coded secret in configs. Secrets shouldn't be passed via environment variables, and of course there should be scanning to detect any exposed secrets in terms of API tokens or passwords or in any sensitive information. So implementing network policies to control traffic within the cluster, and this goes a long way in restricting lateral movement. Say if a certain pod has been compromised, right, and the attacker is trying to spread across the cluster, like we had observed in one of our attack scenarios, implementing network policies goes a long way in restricting that kind of lateral movement. So, more often than not, by default, any pod within a cluster can talk to any other pod. But say a front-end pod might need to talk to a back-end pod, but has no need to talk to or to interact with the storage pod. And those are the policies that we are referring to here. Talking about pod security policies. So running privileged containers or allowing privilege escalation is risky because it lets containers access kernel capabilities of the host. And it also goes a long way in bypassing a lot of the container isolation techniques. And as we saw in some of our attack scenarios, it's also a prerequisite for container escape. Running applications as root. So this is a misconfiguration that I have noticed in many clusters. Now you might argue there might be pods, as in like infrastructure level pods that might need to run with root privileges. True, but it shouldn't be the norm, right? And what's the risk here? Because if a certain pod or a container is compromised, the attacker would now have root level privileges available to them in a platter, right? And we don't want that. Limiting the parameter of containers to read-only file system. And also this goes a long way in limiting the damage in case a container compromise has happened, and it prevents the attacker from writing to the host file system. Similarly, implementing Linux security controls like AC Linux, AppArmor, and SecComp wherever applicable goes a long way in improving the security posture of the cluster. RBAC, fine-grained access control, can be implemented and least privilege ensured via RBAC. And the best practice being, assign permissions at namespace level. For example, implement permissions via role bindings and not cluster role bindings to be able to provide permissions within the context of that particular namespace. So a little trivia here. So this is a snapshot of pod security policy. One is a restrictive one and another a permissive one. Any guesses which one is what? The left-hand side is restrictive or permissive? Guesses? Yep. The left-hand side is a restrictive one, and the right-hand side is a permissive one. As you can see, the privilege flag is set as true. The volumes that can be mounted, it's a wildcard that is set up. So we discussed certain guardrails, right? But how do we make sure that we implement some of these guardrails at scale? So OPA, or Open Policy Agent, was introduced in 2016, and this is meant to provide a unified method of enforcing security policy across the stack. It's domain agnostic and open source. And OPA can be effectively used for Kubernetes admission control. For example, we discussed some guardrails, like not allowing container images to be run from untrusted sources, or pod being disallowed to run as root. And these policies can be implemented via OPA. OPA also integrates directly with the Kubernetes API server, and you have the flexibility of implementing it early in the development lifecycle in the CI/CD pipeline, or just run it ad hoc at a later time to monitor compliance across the cluster. It can also be used for other purposes, like regulating service mesh architecture to implement policies to prevent lateral movement. So we discussed guardrails, right? I mean, what if, in spite of implementing all the guardrails, things go wrong? I mean, would we have enough visibility or detection rules which would be able to alert us on an unauthorized access attempt or compromise scenario? So it is possible to parse Linux system calls and configure detection rules, which might point to us to a compromise scenario. So for example, shell is being run inside a container. Now you might argue this is something that's a normal behavior within my cluster. I mean, my developers regularly use to run shell for troubleshooting, right? What about configuring something to detect reverse shell connection? And as we know, it's popular among attackers, right? Attackers love reverse shells. How about some artifact like a container mounts a sensitive path from the host, such as /proc? And this is a behavior that hasn't been seen in the past, right? Just points to some outlier behavior that gives enough information to pursue an investigation. Similarly, a sensitive file like its shadow and a container has no need to access such a file, but it is being accessed, an access attempt to its shadow. Again, just triggers a detection rule and calls for further investigation. A standard system binary like ls has no business need or any need whatsoever to make a egress connection or an outbound network connection. But if you see such a behavior, that points to an anomaly, right? And as we saw in one of our attack scenarios, I mean, the cryptocurrency miner was named as Nginx, right? So attackers, more often than not, would try to fly under the radar by piggybacking on any system binaries, right? So such behavior fringes on the border of proactive threat hunting, where a process is spawning an unexpected child process, a behavior that hasn't been seen in your cluster or in the context of the pods in the past 3 months or 6 months. Not necessarily it's malicious, but it just gives you a smaller subset of information to do more proactive threat hunting and investigation, and probably point to a compromise scenario. Similar is, a first-in privilege process is spawned. Or, tracking unexpected system calls that can lead to privilege escalations. And the point being, know your environment, what is an anomaly and what is a known good or non-normal baseline behavior. With that context, let's see a basic detection if we can configure via OS query. Now, OS query is just an example in this context. You can use anything that provides you the visibility. So on the upper portion of this screenshot, I have a certain pod, and I'm using wget to reach out to somewhere, to an outbound network connection, and downloading codes, say a malicious piece of code from the command and control server. And this is a very common TTP for more attacks, because at some point, once an initial foothold is achieved and the attacker has escalated privileges, it would reach out to its command and control center to download further malicious code and further information, right? So it is possible to use an OS query statement to detect such outbound network connection. And it's also possible to have more visibility on the command line. Like I can see that the attacker is using a wget command here, and also potentially the domain that it is reaching out to download further malicious code. So to summarize, Kubernetes is complex, and it presents a significant learning curve to secure the workloads that's running in a multi-tenant environment. So Kubernetes was historically designed to be, highly portable, that you can migrate your workloads across on-prem or in cloud services. It's also meant to be highly customizable, as in you need to explicitly turn on certain features to secure your cluster. And it comes with a caveat that needs knowledge of the potential attack vectors and the threat landscape that certain misconfigurations can lead to. And security is hard, right? I mean, the attacker would need to get it right only one time. But for defenders, we need to get it right every single time on multiple levels. So defense in depth approach is essential. And I would categorize it as, pre-fill and post-fill. Pre-fill is something where we focus on the threat modeling or the threat landscape of the entire Kubernetes deployment. And post-fill gives you the security audit logs and some of the detections and forensic capabilities to detect in case a compromise happens. And the bottom line being a defense in depth approach is imperative to secure the Kubernetes ecosystem, as is true for security in general. That's as much time I had for today. These are some of the useful references that helped me a lot when I started learning about Kubernetes and Kubernetes security. And hopefully it would be useful to you as well. And that's as much I had for you. Thanks for your time.